Virtarak is to, yeah.
Yeah, I see, it's recording, okay. So it's always great to have Hugo, who is a wonderful speaker, Hugo Duminil-Copin from University of Geneva and IHES. And Hugo will tell us about symmetries in two-dimensional statistical physics. Thank you, Hugo.
Right, thank you very much. It's a 50 or 1 hour talk? It's 50 minutes plus questions?
Yeah, I guess, but you can, I guess, feel free. People
stop me when you are.
Yes, it's flexible.
Okay, so what I'm going to do during this talk is there is going to be a first part, which is going to be some kind of introductory to a strategy to try to prove what we call conformal invariance. And then a second part where I will tell you a little bit about partial results. And to simplify the talk, I'm going to focus on a very specific model, even though the strategy applies to a large class of models, not all the models we would like, but already a big chunk of them. So the model that I'm going to use for the exposition is going to be Bernoulli percolation. Oh, Bernoulli percolation on Z2. So I'm guessing that all of you already encountered this model. So it's a subgraph of the square lattice with the same set of vertices, and edges of the lattice are open with probability P and closed with probability 1 minus P. If you want, you keep the edges with probability P and you remove them with probability 1 minus P. And I'm going to look at a specific case. I'm going to look always at P equal PC. So we focus on critical percolation, meaning that we will always have, we consider P equal PC, which for the square lattice is equal to 1/2 by the famous Kesten, by one of Kesten's famous theorem, Kesten from 1980. Okay, but the value itself is not important. The critical point, I mean, I hope most of you already encountered a little bit Bernoulli percolation, but for those who never looked at this, when you look at percolation, you can, for instance, ask whether there is an infinite connected component or not in the graph omega, the random subgraph. And there is a critical parameter, PC, above which you have an infinite connected component almost surely, and below which you have no infinite connected component almost surely. So I'm exactly looking at the critical point PC. Okay? And at this critical point, so at criticality, several things happen. In particular, the probability that there exists an infinite connected component in omega is 0. And in fact, you expect, and this is kind of a conjecture, so you expect conformal invariance. So let me tell you what that means. So what I mean by conformal invariance here, in the case of Bernoulli percolation, it can be stated fairly simply. So what we are going to do is we are going to look at omega delta. So omega delta is going to be Bernoulli percolation, but on delta Z2. Okay, so there is a new parameter, delta, which is going to be the mesh size of my graph. And I'm going to look at percolation on this graph. And the thing that conformal invariance means is, what conformal invariance means is that the limit, I will give a little bit more sense to this in a second, but let me state it with a little bit informally. The limit when delta tends to 0 of omega delta restricted to a domain omega, or let's say to a domain f of omega, is the same as f of the limit when when delta tends to 0 of omega delta restricted to omega for every f conformal for any map which is a conformal map. So one-to-one holomorphic map. So say, for instance, conformal from omega to f of omega. So what does it mean, this? It means that, and sometimes the picture is helping here, it means that if I start from a domain, omega, and that I map this domain to another domain, f of omega, by a conformal map. Then here, if I look, or maybe let me put it like that. If I look at percolation on the image by f of the square lattice here, okay, with a very thin mesh size, then the percolation will be very close to percolation on the actual square lattice with very thin mesh size in this new domain. So you see, the percolation on a deformed lattice has the same kind of properties as percolation on the original lattice.
Very close means the distributions are close, right?
Yes, exactly. I'm going to state these things carefully just after, but you are entirely right, yes. So percolation on the deformed lattice, if you want, has a distribution which is very close to percolation on the original lattice, okay? As long as f is conformal. And what I want to be explaining to you now is why you should expect this. That's the first proper thing. And what are the steps? So you are going to see I'm going to state 3 conjectures that correspond to 3 natural steps to try to get to this conformal invariance. And by doing so, I will also state these things a little bit more carefully. And then I will explain to you which steps seem tractable, which steps are still open, etc., etc. Okay? So let's dive into this 3-step approach to conformal invariance. And I'm going to start by maybe stating a little bit more what I mean by this limit and what I mean by omega delta. Because when I take a limit of omega delta is a subgraph of delta z2. But what does it mean to take this limit? Do I want to be considering this graph as, I mean, the limit as kind of graphons, or what do I want to be doing? So here, to simplify our life, there are actually different answers that are possible, but to simplify, I'm going to think of omega delta as a collection of loops. And how do you see omega delta as a collection of loops? So you have the clusters, the connected components in your graph. Think of omega delta as just the collection of loops that are the boundaries of these graphs, of these connected components. Okay? So think of omega delta as a collection of loops. Now there is natural topologies you can think of on the collection of loops. And I'm going to now state the first conjecture, which I call existence of a scaling limit. And this conjecture is going to state the following. It's going to say omega delta converges in low. So I have a set of, so it's always a random variable taking values in collection of loops. I define a distance on the collection of loops. I will maybe come back to this when I will state formally the theorem, but you can think of any kind of natural distance measuring, I mean, that 2 collection of loops are close to each other. If you think about it, you will probably end up with a distance I will define at the end. So you can define the convergence in low for this. So omega delta converges in low to an object, a random variable that I'm going to call omega continuous. I'm going to say as delta tends to 0 to a random variable that I call omega continuous. It's a conjecture, it's not a statement, it's not obvious at all. You are going to see that it's really not obvious. But that's going to be my first conjecture. And I'm going to start, I'm going to work from this thing. Because you see, one thing that you get immediately when you conjecture the existence of the scaling limit is that so omega continuous is automatically invariant under scaling. So omega continuous has the same law as lambda omega continuous for any lambda positive. And this you can see very easily from the following simple observation that omega continuous is the limit of omega lambda delta, right? I mean, it's the limit of omega delta, so it's also the limit of omega lambda delta. But omega lambda delta is exactly omega lambda times omega delta in law, which itself converges to lambda times omega continuous. Okay, so from the existence of a scaling limit, you get immediately, for free, the scale invariance of the limit. In the same spirit, you also get that omega continuous has the same law as tau x omega continuous for any x in R2, where tau this time is the translation by x. Okay? And this is the same thing. What you do is that this is the limit of omega, say, delta over 2 to the n, where x belongs to delta z2. Then this has the same law as tau x omega delta over 2 to the n, because I am assuming that x belongs to delta z2. So already the translation by x is a symmetry of the original model, and this converges to this. Okay, so you get translation invariance and scale invariance for free. Now comes a second conjecture, which is much less obvious, at least to my opinion. So this is conjecture 1. Now let's mention conjecture 2. And this is maybe more surprising the first time you see it. And it's the rotation invariance of the limit. These conjectures, by the way, they are absolutely not due to me. They are rather due to physicists, maybe not in the way I'm stating them, but definitely this is something that physicists would predict. I mean, there is a little bit of this, things necessarily converge in nature. So, I mean, this omega delta has to converge to something. It's a very natural conjecture. And from this conjecture, they build up and created this second conjecture, this rotation invariance, which is much less obvious. So omega delta has the same law as rho theta omega delta for any theta in R. Obviously, I would have told you that only for theta, which is in pi over 2z, it would not have been a very deep theorem, but I'm telling you that this is true for any rotation. Okay? And that is a conjecture that really you can call a conjecture in the sense that it's a non-trivial prediction. Okay? And let me tell you briefly, extremely briefly, why physicists expect this, because it's a very nice argument, even though it is based, from my point of view, on an assumption which is much stronger than the conjecture itself. So the idea of physicists would be to invoke what they call the renormalization group. You probably already saw this RG, they call it RG. And the idea of the renormalization group is to think that the map, the rescaling by a factor this time lambda, which is maybe smaller than 1, is the same as applying a map on the space of models. So rescaling a model is like applying a map on the space of models. So it gives you a new model, the rescaled model, and this is imaged by this map of the original model. Okay? But once you have this vision on the rescaling operation, you have a very nice consequence of that, which is that omega continuous is the limit when n tends to infinity of t lambda to the n omega 1. Why? Because it's a limit, let me maybe add one sentence. So it's a limit of omega lambda to the n, which is the limit, which is exactly by definition, iterating n times the rescaling operator applied to the original model, omega 1. So up to now, I just rephrased, in some sense, my limit as a dynamical system, but what you get for free from that is that omega continuous should be a fixed point of this rescale operator. And then here is the prediction, and beautiful prediction of renormalization group, at least in our context, that there exists a unique fixed point. But if you have a unique fixed point, then if you start, so omega continuous is indeed, so if you start from omega 1 and you iterate t lambda, so iterate, you end up with omega continuous. But if you start from rho theta omega 1, so just the model on the rotated lattice, and you iterate t lambda, then you end up with a fixed point again. But if there is a unique fixed point, that means you end up with omega continuous. And that tells you immediately that omega continuous has the same law as rho theta, maybe rho minus theta in this case, of omega continuous. Okay? But I would like to highlight one thing, which is a little bit unsatisfactory with this, with this argument, is that the uniqueness of the fixed point is absolutely non-trivial, right? It's, I mean, we know many dynamical systems, fortunately for us, that have many fixed points. So here, there is a very strong assumption that indeed implies rotation invariance, but which is absolutely not clear to start with. Okay? So that's conjecture.
You also have to say in what context you mean unique fixed point. I mean, there are more processes which have this invariant, right? I mean,
yeah. I mean, in addition to that, you need to really, I mean, restrict at the beginning, indeed, the idea. I mean, that's exactly what a physicist will answer to you. So you will tell him, I mean, obviously the system doesn't have a unit fixed point because I can construct, you know, this fixed point and so on. And then they will add sufficiently many assumptions that it becomes reasonable that there is a unit fixed point. So you can always restrict the space of models on which you work to get a fixed point. I must say, I'm not contradicting the renormalization group. It's a beautiful picture, but I just want to be highlighting that at least the assumption of unique fixed point is at least as strong as the assumption of rotation invariance. Okay, third conjecture and last conjecture. Well, it's kind of a wrapping up conjecture, wrapping things up, which is just going to be to prove that that translation invariance plus scale invariance plus rotation invariance, well, these things imply conformal invariance. Okay? And this at first sight, it could look very bad. I mean, this could look like a very difficult conjecture. And actually, I would say that this is probably the simplest step of the three, surprisingly. Ironically, that's not the step we proved, but I mean, we had an almost proof a long time ago already. We don't manage to turn it into a full proof, but I'm sure that people that are smarter than us will manage to do it. So let me give you the heuristic, at least for percolation, because it's a fairly, I think, oh, there are questions. Oh, okay. Okay, let me just finish my sentence and then I will answer the questions. So, or maybe I answer the question and then I tell you that. So can you remind me what omega delta is? So it's percolation on delta Z2. And then Clay, why omega ln is in conjecture 2, but not omega continuous? What did I say in conjecture? Ah, no, it's in low equal to this. Ah, yes, omega continuous. Now I understand. Yeah. You are completely right. It's just a typo. Yes, it's omega. It's only the scaling limit, which is rotationally invariant. The model itself, omega delta, is not rotationally invariant at any delta. That's a very good comment. Thank you very much. Okay, so let me give you a heuristic for Bernoulli percolation, but it applies actually to a wider class of models for this conjecture 3. So the idea, I'm not going to say much, but maybe some of you will already be partly convinced. So the idea is, let's take a box of size 1, okay, and let's try to focus on what happens in the box of size 1. So remember that the mesh size is tiny, okay? So what I'm going to do is I'm going to fix an epsilon. This is much smaller than 1, but again, I'm insisting delta is going to tend to 0 eventually, okay? So delta is much smaller than epsilon. And what I do is I partition my box into small squares of size epsilon, okay? You will agree with me that in each one of these boxes, let's say this is Zi, Zi is the center of the box, f of z looks like fzi of z, which is going to be looks almost like fzi of z, which is f of zi plus f prime of zi, z minus zi, like the linear approximation centered on zi, right? Because it's a conformal map. This application, by the way, is the composition of a rotation, a translation, and a scaling, right? This is exactly what you get for free from the fact that f is conformal. And this approximate here is kind of second order approximation in z minus zi. So now imagine you have boxes of size epsilon. That means that at least when you stay, if you use, so this is Zj, if you use the approximation from f by the linear approximation, well, the image by f of delta z2 is going to look very much like the violet lattice here, which is the image by f zj of the original square lattice. But fzj is a composition of rotation, scaling, and translation. So this violet guy, which is close to the green guy, is just a rotated and rescaled version of the square lattice. So if I have already translation, scaling, and rotation invariance, I can replace for free, when delta is tiny, I can replace for free the violet guy by the original red guy that I want to compare to, right? I want to compare the green lattice to the red lattice. So by going through this violet lattice, then going from violet to red is trivial. And I can do this approximation in all the boxes. I always pass by the corresponding linear approximation, and then I couple with the original red lattice. So where is the catch? Why isn't it this almost a proof? Well, there are two problems, right? The first problem is that the green and the violet guy are not exactly the same lattices, right? They are close to each other, but up to an error, which is of second order, very good, but it's not an exact coupling. That's the first thing you do. The second problem is that here, at the border, I'm going to do two different approximations. On the left, I'm using the linear approximation in this square, and on the right, the linear approximation on the other square. So there is also a kind of matching of things that is not obvious at the boundary. But for people who know a little bit more about percolation, it is possible to prove that there is no information at the boundary between these two things. It's called a black, sometimes it's referred to as percolation is a black noise. There is no information to reconstruct there. So you can believe that maybe reconstructing here is not going to be too difficult. I can indeed do the patchwork if you want, in any of the boxes, and then reglue together into one nice picture. And the main difficulty is actually going to be to control this second order error. So we managed to do it under an assumption, and this is just a parenthesis. If you didn't hear about this before, do not think about it. So we know how to do it under the assumption that alpha 6 minus alpha 5 is larger than alpha 5 minus alpha 4. So the probability of having 6 arms knowing that you have 4 is much smaller than the probability to have 5 arms knowing that you have 4. 6 arms knowing that you have 5 is much harder than having 5 knowing that you have 4, which is very natural to expect, right? The more arms you already have, the harder it is to get an additional. This is for people who knew about percolation. If you didn't hear, you didn't know enough, this is just a parenthesis. You can forget about all of this. So we have other assumptions, by the way, that we can replace this assumption that I just stated by, which are maybe even weaker, but I mean, I don't want to be spending too much. So bottom line at this stage, the bottom line is the following. Conjecture 3, I would really be surprised if this cannot be done. And I think this conjecture is going to be done by somebody in the next few years. And I'm pretty confident. So this is probably doable. And of course, I'm insisting on the probably in the sense that, I mean, you can never expect. What are the alpha? So alpha are the critical, the arm exponents. But I mean, maybe just ignore this comment. That's just let's jump over it, and we will not use it at all for the rest of the talk anyway. Okay, so conjecture 3 is probably doable. Conjecture 2 looked like this would be very bad, but actually this is the content of the theorem. So you are going to see it's proved, and this is exactly the subject of the seminar. So that leaves conjecture 1 as really is the main remaining open question. So a physicist would already probably be happy because he would say, okay, that proves that any limit is necessarily conformally invariant. As a mathematician, we would prefer to be able to state the existence of the limit. So this conjecture is really an important step of the whole process. And as for now, I don't know how to prove it. And maybe I can tell you a little bit more why why there is a difference between conjecture 1 and 2, for instance. At this stage, it's also important to state 2 remarks that are quite important. And then we will dive into the proof of, the formal statement of the theorems and a little bit of the proof. So the 2 remarks, the first one is that this is conjectured for many models. I kind of explain through the case of Bernoulli percolation, but for instance, it should be true for Fortuyn-Castellani percolation, for the Potts model, for self-forwarding walks, for loop-ON models. There is a vast variety of models that all should get the same behavior. And the second conjecture, the second remark, and it's a very important one, is that sometimes conformal invariance was proved by mathematicians. So some models were proved to be conformally invariant. Only few of them, not that many actually, but still beautiful examples of the strength of mathematicians, because the strategy by which these models were proved to be conformally invariant is not really following this 3-step procedure. It's not at all kind of following what the physicists were expecting. It's kind of a direct proof. And basically you find kind of relevant observable of your system and you prove directly that these guys converge to a conformally invariant object. So you really shortcut completely the original strategy of the physicist. By the way, the physicists for Conjecture 3 don't refer to it as, I mean, it's not at all the argument I described to you. They would just say this kind of very short sentence, which is, well, the limit should be described by a field theory that is local. So, you know, any function that is locally a composition of rotation, scaling, and translation should be a symmetry of the, and they are right, but this is maybe a little bit harder to believe than this kind of sketch of proof that I gave. Okay, so some models were proved to be conformally invariant, and let me mention one because I decided to focus on Bernoulli percolation. So Smirnov in 2001 proved conformal invariance of a Bernoulli percolation model, but it was side percolation, meaning that instead of keeping or removing edges of your graph, you remove vertices, or you keep vertices of your graph. And there is also a critical point. You are on the triangular lattice, and at PC, you have conformal invariance.
Sorry, what are alphas above? Alpha 4, alpha 5?
They are the critical exponents for the arm events. But as I told you, please disregard this comment if you never heard about it. This was kind of something to chew on for people that know a little bit more about Bernoulli percolation. But really, don't bother. We will not need it later.
Thank you.
Okay, so the result now.
Oh, can I ask a question?
Yeah, of course.
Does this tell you something about the near conformal invariance of near critical percolation, say, or something?
So when you are off critical, you are not conformally invariant anymore, but you should be rotationally invariant. I mean, what you lose is scaling. And the rotation invariance will follow from the arguments, yes. I mean, combined with other works that we did on scaling relations and things like that. So I think we should be able to get the rotation invariance of the near critical scaling window, yes.
Thanks.
Okay, so what is the result? So theorem. So it's a theorem, there is a big, long list of myself, Dima Krashun, who is a PhD student in Geneva, Karol Kozlowski, a physicist from Lyon, then Johan Manulescu, that most of you know, from Fribourg, and Mendes Ulamara, who is also a PhD student, but this time in IHES. And the result, I'm going to state it first for Bernoulli percolation. It tells you the following. It says there exists a constant C such that for any theta in R and any delta in positive, there exists a coupling, let's call it P, such that the probability, so a coupling between omega delta, which is sampled according to Bernoulli percolation on delta Z2, and omega prime or omega bar delta, let's say, which is sampled according to Bernoulli percolation on E to the I theta. Let me maybe use delta here. The mesh size, and theta is the angle. Z2. So you can couple Bernoulli percolation on delta Z2 and Bernoulli percolation on the rotated version of this guy, such that the probability is that the distance, and I know I didn't tell you what the distance is, I'm going to tell you in a second. So the distance between omega delta and omega bar delta, the probability that it's larger than delta to the C is smaller than delta to the C. So with very probability very close to 1, the distance between the percolation and the rotated version of it in the coupling is small. Okay? And let me tell you what the distance is. The distance here, you can choose basically any distance you would like to. So there are at least 2 natural distances, and I'm going to describe one of them and just mention the other one. So the other one is the Schramm-Smirnov distance. for people who know about it. And the distance I'm going to describe now, which we call the Kamian-Newman distance, but Newman was not so happy about it because apparently they never introduced it, but is a distance that is the following. You want to say that two collection of loops are close to each other. If for any loop in the first guy, you can find a loop in the second collection that you can parameterize. You can parameterize the two loops in such a way that they remain at distance epsilon of each other along the whole thing. Like, okay, so, and you said that you are small if all the loops in the first collection have a loop in the second that is close to each other. It's really, I mean, if you think about it, you are going to end up with this distance. I mean, this is really the natural distance to measure distances between collection of loops. Okay? So the what we call the Kamian-Newman distance. Here, it's good to mention a few things. So this theorem is actually a theorem which doesn't involve omega continuous in the statement, right? It's something about omega delta. It's actually a quantitative kind of rotation invariance, okay? But of course, it does imply something, which is that any subsequential limit of the collection omega delta is rotationally invariant. Okay, so if you want, you don't really need conjecture one. You can just take subsequential limits, and any subsequential limit will be rotationally invariant. Okay. Second thing that is important here is that it applies to all FK percolation with Q between 1 and 4. So this is, again, maybe I should have put it in green. This is kind of a parenthesis for people who know a little bit more. You can, for the others, you can switch off for a second, just the time to state a little bit this thing. So here it applies for a general version of Bernoulli percolation, if you want, with dependencies, which is a natural, actually, percolation model. And it applies in a range of parameter Q between 1 and 4, which is not quite optimal. Normally, it should be between 0 and 4. But between 0 and 1, we have a problem of lack of correlation inequalities. So even the existence of the critical point is not clear at this stage. Okay? But 4 is optimal, meaning that for Q larger than 4, you don't have a rotation invariance. It also applies for, because I know that some people like this very much, and among these guys, to 6 vertex models. And here we believe, and this is not yet proved, it's a student who is doing it, but with A equal B equal 1 and C larger or equal to 1. So this should be actually a kind of C between 2 and 1. And again, it should apply for every C larger than 0 up to 2. But we have a problem of correlation inequality, and we can do it only for C larger or equal to 1. It also applies for people who like this model to the POTS model with Q equal 2, 3, or 4 colors, etc., etc. So you have a bunch of models for which you can prove rotation invariance. We believe that, for instance, for loop ON models, it would probably also work in a certain range. So there are a bunch of models for which you can follow the same type of ideas and prove the same theorem of rotation invariance. Okay. So in the last, let's say 10 minutes, maybe a little bit, 10 minutes, let me tell you a little bit about the proof. But really, I mean, it's going to be very, very, very quick. So funnily enough, or interestingly enough, the proof is not going to be a direct proof of rotation invariance, if you want. The key of the whole argument is what we call a universality result. So we prove rotational invariance, so we prove rotation invariance by proving what we call a universality Universality Result, which is the following. So imagine you want to prove at the end rotation invariance by an angle theta. Okay? So what you are going to do is you are going to define a rectangular lattice, a little bit squeezed. Let me not tell you why, but a squeezed rectangular lattice which is rotated by an angle theta. Okay? And this squeeze, so here you have a certain distance L theta and here L prime theta, which is different. Okay? And what I'm going to do is I'm going to open edges here with a probability p theta, and I'm going to open edges here with probability 1 minus p theta. And p theta is a functional, it's a parameter, sorry, which can be computed in terms of theta. There is a formula, even me, I don't remember it by heart. That's not so interesting, but there is a parameter theta for which there's natural parameter theta to take. So now my goal is going to be to prove that there exists a coupling. So let's say I take omega delta on this lattice. So I'm not taking the square lattice like that. I'm rotating it just because I'm used to that. Okay. So the square lattice is kind of the rotated version of this thing. And what I'm going to do is I'm going to find a coupling P between omega delta and omega tilde delta, which is defined on delta times this graph. Okay, so here it's on delta Z2, or actually to be more precise, delta e to the I pi over 4 Z2. And here it's going to be on delta times this graph. Okay? And when I mean by a coupling, I mean, I'm going to call it a truthful coupling. I just mean a coupling that satisfies this property. Oh, sorry. So I'm going to couple in such a way that the loops in the two models are very close to each other. I'm not telling you yet how I find this coupling. This is going to be exactly the work to find this coupling P. But imagine I can find this coupling P. Then here,
you do this for every theta or what?
Yes. So I do this for every theta, but by the way, here you already fix theta at the beginning of your proof. So in some sense, for every theta, there is going to be a proof of rotation invariance. You don't need to prove, of rotation invariance by an angle theta. The different theta don't talk to each other. Okay, so we fix theta. That's a very good comment. And we do that. So now in this model here, you observe that you have an axis of symmetry. Okay, so omega tilde is naturally coupled with the symmetry by an angle theta over 2, maybe something like that, of omega tilde delta. And there it's a trivial coupling. It's just using the symmetry of the model. But then this model is still a model on delta times my lattice like that. So I can reapply my truthful coupling P to end up with something that is going to have the distribution of the symmetry by an angle theta over 2 of omega delta. But because this guy also has the same symmetry, the same law as just the symmetry with respect to the x-axis, I just ended up with the fact that sigma 0 omega delta is almost, through this coupling, this chain of 3 couplings, is almost perfectly coupled with the symmetry with an angle theta over 2 of omega delta. So if I erase this guy and put it here, I end up with rho theta. So why do I call it a proof of rotation invariance by proving universality? Is that here what we do is that we are proving that, let's ignore this thing for a moment, we are proving that percolation on delta Z2 has roughly the same law as percolation on another lattice. It's exactly a universality result. saying that if you take two different lattices, you have almost the same law. So now let me very briefly in the 2 last minutes tell you how we construct this coupling, because up to now, you can make, I mean, this is just a rephrasement of the original question, but I mean, maybe finding this coupling P between percolation on delta Z2 and percolation on this rotated version of the rectangular lattice, maybe finding this guy is as difficult as the original question. So I'm claiming it's not the case. And the reason for that is that it's known for some time that among a large class of graphs that are called isoradial graphs, there is a natural transformation, which allows you, so let me just make a parenthesis here, which allows you to transform percolation on a graph where you have a triangle somewhere, so just a face of degree 3, into percolation on exactly the same graph, except that instead of having a triangle, I replace it by a star. This is something that you probably saw in other contexts, in particular in electrical networks. You can modify an electrical network by replacing stars by a triangle by stars, and this is very useful to kind of reduce your electrical network to compute the resistances. Well, percolation model, and more generally, many models that satisfy the Yang-Baxter equation, they also have this kind of transformation, this star triangle transformation, allowing to modify one graph into another one. Okay? So why did I choose this rectangular lattice with a special choice of p theta and 1 minus p theta? Because these guys, when I put the square lattice and that I put the rectangular lattice on top of it, I can, by star triangle, transform this graph into a graph where I have the rectangular lattice below and the square lattice above. Why is it good? Because now imagine that I can prove to you that this star triangle transformation, they don't modify substantially the shape of the loops. Then if I start from a percolation configuration here and I apply the star triangle transformation, notice that, I mean, just to mention to you, if you take a box n by n, you will need to apply n cube transformation. So it's a long process to modify one graph into the other one. But what you will end up with at the end, if you can prove that the loops are not altered too much by the star triangle transformation, you will end up at the end with a collection of loops, which is very close to the original one. But here I was on the rectangular lattice, and now I am on, on the square lattice, and now I'm on this rectangular lattice. Okay? Just to conclude, a word here. So the star triangle transformation in terms of loops only modify loops marginally, in the sense that it doesn't modify the loops outside. It's maybe just here loops that kind of intersect this triangle, maybe modified just in the triangle. But we do n cube transformation, so these loops, they could a priori really move. So the whole difficulty of the proof is to prove that indeed they do not. Okay, and there is some nice probabilistic arguments defining kind of the speed of the transformation, and then proving that this speed is 0 to just prove that by ergodicity these things do not move. But this would require too much details and too much information, so I'm going to stop here. Toda raba.
Okay, thank you, Hugo. Questions, I guess.
Where the n cube comes from?
Sorry, when?
Where the n cube comes from.
Because in fact, what you are going to do when you transform this thing, you are going to pass one line of the lattice down by 1, then 1, then 1, then 1, then 1. So to bring it back to the bottom of the place where you want it to be. Then you take another line and you bring it down 1 by 1 by 1 by 1 to there. So you have n tracks and n lines that you need to bring down by n steps. Okay, so you have n squared kind of bringing down a track, and to bring down a track, you need to basically what you are going to do is you are going to modify a little bit here the lattice to create a triangle, and then you are going to use track exchange to, you are going to use star triangles to kind of exchange the two tracks. Maybe I can make just one drawing that is going to be helping. So let's say this is not the square lattice. The square lattice is going to be there. So this is the square lattice. And let's say this is the bottom of the rectangular lattice. And what I'm going to do is I'm going to add, imagine like at infinity on the right, I add this guy like that. So now here, I have a triangle. So I can do a star triangle exchange. And when I do that, I'm going to end up, so let me re-put like that. I'm just doing one, but maybe it kind of gives you an idea. So these things are not changed. But here, when I do a star triangle transformation, I'm going to end up with the following star, which is going to be this star like that. So I change the triangle into a star. Now here, I have a star, I can exchange. So let me do just one more step. And then I think you would have understood what is going to happen. So if I do one more change, I end up here with something that is going to be like, so let me draw in yellow. So this star here, I exchange it into a triangle. And now I have a triangle here. I can keep going like that. And you see your star triangle transformation apply more and more on the left. But the important thing is that here now, you have exactly what you had here. And this thing now is below. So you kind of, if you imagine doing that up to the end, you are going to end up with a picture where you started like that. And at the very end, so you start your star triangle transformation from the right, you go to the left, and at the end, you are going to end up with something that is going to look like that. And here, you are going to have, or maybe, yeah, something like that. So you exchange the two tracks. So exchanging two lines costs you n transformation, basically. So that's the n cube. N transformation by exchange, I have n tracks to go down by n steps. So this gives you n cube.
Oh,
What
okay.
is the limit object, omega continuous? Omega continuous, what is it?
Yes, so at the end, once you have proved conformal invariance, so you have this kind of random variable taking values in collection of loops. And it has actually a well-known law. So once you prove conformal invariance, it's always like that, right? You prove so many symmetries of your object that you can start describing the object with few parameters. So there is a one parameter collection of random variables taking values in collection of loops, which is called the conformal loop ensembles. So here, so the conformal loops ensembles, they are called CLE. And for percolation, it's series 6. The limit. It's a very nice collection of fractal non-intersecting loops.
Thank you.
Non-crossing loops, sorry. They are intersecting loops. Well, thank you very much.
No more questions? Okay, thank you again to Hugo. It was a wonderful talk. Thank you.
Thank you, Hugo.
Very much.